All right, everyone. So I hope that you tried to solve the problems. Okay, tell me, how did you find it? Any trouble? Any particular confusion problem? Hello, are you there?
Yes, sir.
Yeah. Yes. How did you go about it? Okay. All right then. So let's start our discussion.
Sir, should we tell the answers?
No, I don't really want to know the answer. I want to know if you have any problem trying to solve the problem, because it would be easy for me to focus on this problem and discuss it a bit more. Anyway, I'm going to solve all
Mm,
those problems.
No, sir, I don't have any problem.
Okay, fine. Very good. Okay, let the Ajan finish. So first of all, I'm going to solve the second problem, because the first problem is essentially the same problem that it has been delivered in the class. So remember, in the lecture, we said that there are two ways we can obtain full wave rectification. One of them was full wave bridge rectifier, the one that we have already discussed in our lecture, and this is the second one, full wave rectifier with full wave full wave with so this is a full wave rectifier with center tape transformer. First of all, we're going to describe what transformer is. So I think you have pretty much some idea about the the magnetic circuit. So if you remember the magnetic circuit that you learned in EEE 201, I'm just going to give you a brief review of the magnetic circuit. So it's a it's a metal core which consists of a magnetic circuit. Metal core which has 4 arms. Okay, and then if you have wire winding this side, and also wire ending this side. So that means this is copper wire. You own the left leg of the magnetic circuit, and you have copper winding, which has been owned to the right leg as well. What happens is that if you apply an AC signal here, okay, let's say you apply signal I, and so let's say VI, so Vm sine omega t. So if you apply a signal, there will be a current I. Let's say the current is Im sine omega t. So that means a current will be flowing. Now notice the current itself is what? Sinusoidal. The AC signal is sinusoidal, the corresponding current is sinusoidal. So that means we have a sinusoidal current flowing through the circuit. Now if you remember from your magnetic circuit concept, or also from physics, intermediate physics or A-level physics, that when a current is flowing through a wire, so let's say a current is flowing through a wire from position A to position B, it creates a magnetic field around it. Okay? And the magnetic field, the direction of the magnetic field can be expressed using the right hand rule. So that means if you curl all the fingers except the thumb, and the thumb is pointing in some direction, let's say in that case, if the thumb is directed towards the direction of the current, and the rest of the fingers which has been curled is the direction for your magnetic field. So that means if the current is flowing is in this direction, the magnetic field is perpendicular the magnetic field plane. If you consider this circle, it's a plane. This is perpendicular to AB, and this is the direction. So that means the current through a wire creates a magnetic field. So that means magnetic field means magnetic flux, which is also called phi. Okay, phi. Now, if the current is constant, the magnetic field will be constant. But if the current is changing, what will expect? The magnetic field will be also changing. So that means if you have a changing current, so you can expect the magnetic field or magnetic flux, which is expressed as phi, it will be also changing. And magnetic field is always complete. So that means it will be like that. If you remember, so this is the direction. If you apply right hand rule, this is the path for the magnetic flux or magnetic field phi. Now, if the current is changing, it's AC, that means the magnetic field itself will be changing. So it's going to have this pattern. That means the flux will be starting from 0. As time changes, it will go to maximum, and then it will come down to 0. Again, it goes to negative maximum. So that means if the direction of the current changes, the corresponding magnetic flux will be changing as well. So some positive half cycle is going in this direction, negative half cycle is going in the other direction. So far, so good. Now notice this magnetic field which is circulating about this coil, about this core. Now it is when it is passing through this right leg of the core, so it links the magnetic flux to this copper winding. So if you have a magnetic field, okay, so if you have a magnetic field something like that, and then you have a copper winding. And if you, let's say, or if, let's say, for example, you have a magnet, simple magnet, north, south, and if you move the magnet up and down, keeping the copper wire constant, so we know that we're going to have a changing magnetic field. So the copper wire is going to experience different strength of magnetic field, because if you bring the north side closer to the coil, so the strength of the magnetic field will be higher. If you take it away, strength of the magnetic field will be lower. So that means the copper wire is experiencing a changing magnetic field. Now we know that if you have a changing magnetic field, it is going to induce what? Can anyone say?
Current.
EMF.
Oh, EMF. EMF.
You know, according to Faraday's law, what is the EMF should be? Can anyone say?
Sir, N d phi by dt.
d phi dt. Yeah. Of course, there is a n. If the numbers of turn is 1, then n should be 1. If the number of more turn, then n should be. And we know that there is a minus sign. For the time being, we just ignore the minus sign. And minus sign is due to what?
Lenz's law.
Lenz's law. So you know those things. So which means, what I'm going to find out? We're going to find out that there is a EMF generated. Let's say V0. That means there is no direct physical connection between this side and this side, only through magnetic field. So when you apply some sinusoidal voltage, you are going to find the output sinusoidal voltage. So this side, we call it primary side. That is secondary side. So there is a relationship between Vi and V0. V0 over Vi is, in fact, is proportional to the turn ratio. If let's say if it's the turn, numbers of turn is N2 and this numbers of turn is N1. So in that case, should be N2 divided by N1. Okay. So the output voltage of the secondary, output wave shape at the secondary, whether it is higher or lower, it depends on N2 divided by N1. Now if N2 divided by N1 is greater than 1, what does that mean? So that means V0 will be greater than Vi. You know, the voltage would be greater than Vi. For example, let's say its amplitude is the 10, okay, and turn ratio is N2 divided by N1 is equal to 2. So which means if Vi is equal to 10 sin omega t, what should be V0? 2 into Vi, which is 2 into 10 sin omega t, which is 20 sin omega t. So that means amplitude for V0 is twice as much as the amplitude for Vi. So this way, if you have higher voltage in the secondary, it is called step up transformer. And if the voltage, if you have a lower voltage at the secondary, it's a step down transformer. Okay. So transformer, you see, you know, you know the term transformer. You see it if you, as soon as you go outside. So in the supply line, it could be, let's say, 11K or 220 volt, whatever the voltage, 11K. But at your home, they don't deliver 11K. 11 kilovolts. So they do deliver you 220 volt. So how is that done? It is passed through a transformer which will step it down. So that's what the transformer does. Now, that's what we have. Now we have a transformer where we're applying the input signal Vi here. and then the output, the secondary, from the secondary, we get the output signal, and the turn ratio is 1 to 2. So that means N2 divided by N1 is equal to 2. So which means if you apply a signal Vi, V0 is equal to 2 Vi. Okay. Then we completed the circuit. So from this side we have D1 and D2, and from the middle of the transformer, for example, if we go down here, you can say from the middle of the transformer we take a connection out. So you can say the circuit looks like this, and from the middle, tapping here in the middle of the, we have something like that. So that's why it is called center tap transformer, because the central part of the transformer is tapped and make a connection. It's R, and the voltage or the output wave shape is obtained. Let's say this is VR. If I already said V0 is the output voltage, yeah, VR. So VR is the output voltage. So that is mean that the voltage that we are going to obtain here. Now, so this is the whole circuit arrangement, and we want to find out the output wave shape, which is measured from across the resistor for this signal. So let's explain how we can obtain this thing. So again, it has two half cycle, positive half cycle, negative half cycle. So let's say at first we consider for positive half cycle, and it's valid from t is equal to 0 to t by 2. So Vi is greater than 0 in this. If it is Vi, it will be 2 Vi. Output would be, in the secondary, we're going to have 2 Vi. Now this 2 Vi voltage at the secondary is equally divided in half, because connection is taken from the center. So in the upper half, we're going to have Vi, and the lower half, we are going to have Vi. So this way, the total voltage from here to here, we have 2 Vi. So that means upper part of the circuit, which consists of the resistance and the diode D1, is experiencing Vi signal. Also the lower part of the circuit, which consists of resistance and the diode D2, is also experiencing Vi signal. Now, for lower part of the circuit, we can see the positive terminal of the signal source is connected to the N side, and the negative terminal of the signal source is connected to the P side. So that means this appears to be reverse bias. Now, if this appears to be reverse bias, so we can say it is reverse biased. So it's reverse biased. So that means that part of the circuit is not working for this positive voltage. So in that case, we can redraw the circuit like this. And this is open circuit. So doesn't matter whether you have it or don't have it. Now we are going to go for the usual procedure. First of all, we're going to determine the transition state voltage. So let's say so plus minus Vi T1 R. So first step would be determining the transition state voltage TSV. Okay. At TSV, and we know that at transition we're going to replace the diode with 0.7. And the current through the diode I is equal to 0. So if I apply KVL, we get Vi plus 0.7 minus IR sorry, not plus, it's a minus over, is equal to 0. This I is equal to 0, so that gives us Vi is equal to 0.7. So I know the transition state voltage is 0.7. So now if I go back here, so I'm going to do what? I'm going to draw the transition state line. Which is Vi is equal to 0.7. Now we know that once we have obtained the transition state line, what information we can extract from this transition state line? We know that transition state line gives us the boundary between the on state of the diode and the off state of the diode. And how could we find out which one is on state, which one is off state? We said that keeping the signal to our left, we keep the signal to our left and we check the orientation of the diode. If it is clockwise direction, in that case, for all the signal, all the value of signal above the transition state line, diode will be on, all the off. Okay. So we know that above on, below off. And as before, we are going to do this 0 to T1, T2. So which I can write that for 0 to from 0 to T1 and T2 to capital T. T is greater than 0, less than T1, and T is greater than T2, less than T by 2. You see, we are below the dotted line, so diode is up. So that means Vi is less than 0.7, diode is up. On the other hand, T is greater than T1 and less than T2. We are in, all the value of the signal is above the dotted line. Vi is greater than 0.7, diode on. So we know the time interval when the diode is off. This is the interval diode is off. This is the interval when the diode is off, and the interval when the diode is on. Also in terms of voltage. So next thing would be to draw the input-output relationship. So let's draw the input-output relationships for both on and for off. When the diode is on, we can replace, and we know the diode is on between this interval when Vi is greater than 0.7. So we can replace the diode with 0.7. And current is non-zero. And this is the voltage drop R. So VR plus minus. So if I apply KVL, we get plus Vi minus 0.7 minus VR equals to 0. So VR equals to Vi minus 0.7. So this is the input-output relationship when the diode is on. Let's find out the input-output relationship when the diode is off, and that is valid where for T is greater than T1. Sorry, T is greater than 0, less than T1, and T is greater than T2, less than T by 2. In that case, diode is off, which means we can replace the diode with open circuit. So the current I is 0, which means VR is equal to 0. So that means the input-output relationship when the diode is on. So let's say 0 to T1, diode is off, so output is 0. T2 to capital T by 2, diode is off, output is 0. And V0 is equal to Vi minus 0.7. So that means that output is going to take the same shape as input, except that it will be dropped by 0.7. So output is going to take this shape. So, and the peak would be, if Vi is equal to Vm, peak would be Vm minus 0.7. So that is the output. It looks like for positive half cycle. Now, next, once the positive half cycle is over, then comes what? The negative half cycle. So let's see what happens during negative half cycle. Okay, negative half cycle. So negative half cycle, first of all, our polarity is what? Positive or negative? Since we are doing it negative half cycle, that means polarity is negative. So that means if there's a Vi, we have 2 Vi here as before. The 2 Vi divided in 2 half, in the upper half Vi and the lower half Vi. So that means if you so which means that if you analyze the upper circuit and the lower circuit, you see the D1, P side of the D1 is connected to the negative terminal and the N side is D1 is connected to the positive terminal. So that means D1 appears to be reverse bias. And if D1 is reverse biased, we can get rid of this thing. So that, which means that we can effectively draw the circuit like this. Plus, minus, Vi, D2. So that means we don't need to worry about this part of the circuit. Again, we're going to go through the same procedure. First of all, TSV. At transition, we know that Vd is equal to 0.7, I is equal to 0. So let's do this. So okay, so at transition we have (0.7) and the current I is equal to 0. So if we apply KVL, then we get minus Vi minus IR, or let's say current is flowing this direction, so plus IR plus 0.7 equals to 0. So that gives us Vi is equal to 0.7. Now Vi is equal to 0.7. What does that mean? I am asking you all. So Vi is equal to 0.7. What should I'm going to draw the transition state line. আমি কিন্তু আপনাদেরকে জিজ্ঞেস করছি। This is very critical. No, not crucial. I should rather use the term. So tell me.
Yes, sir.
Yes, sir.
Okay. So Yeah, someone said negative side. Why negative side? Can anyone tell why it is in negative side? The reason, although Vi appears to be positive, but we are going to draw it. When you're going to draw it, we're going to draw it here. We're going to draw it here. Why? Because at the very beginning, you know, you have already considered the signal is negative. We have already considered when we are doing the KVL, we already consider that our signal is a negative half cycle. So the only thing I know where I am, I know that I am in the negative half cycle. I am not in that positive half cycle. I am definitely, I know I am in negative half cycle. So since I know I am in negative half cycle, so whatever the value I am going to draw it here. So it should be Vi is equal to minus 0.7. But if when you write it, it should be again. We're going to T3, T4. Okay. So if I redraw the circuit here, so that means T is greater than T by 2, less than T3. Now, sorry, I should go back. Yeah. So that means it tells us that since the diode, you know, oriented in anti-clockwise direction, you see, the diode, if you keep your signal source to your left, and the orientation of the diode is anti-clockwise direction. So D2 is anti-clockwise direction. Now you already learned that if it is in anti-clockwise direction, for the value of signal below the dotted line or below the transition state voltage line, diode is on, and value of the signal above the transition state voltage line, diode is off. So that gives us T is greater than T by 2. So from here to here, and less than T3, and from here to here, T is greater than T4 and less than T, the diode is off because Vi is greater than minus 0.7. On the other hand, between T3 and T4, T is greater than T3, T4, all the value of signal is below that dotted line, transition state line. So that gives us Vi less than minus 0.7 volt, the diode is on. So I know when the diode is on, I know it is when the diode is off. Diode is off, and I know this is when the diode is on. So again, I know the off and I know on. Now I'm not going to do it for off. I know that when the diode is off, current is 0 through the resistor, so voltage drop is 0. So I'm going to do it for on. So for on, let's redraw the circuit. And let's consider the diode is Vi already negative R, and the current is flowing in this direction. Real current. One thing you must remember, the real current, so if this is the real polarity, plus minus, the real current, always real current, not the assumed current. Always flows from positive to negative terminal through external part of the circuit. So that means this is the source and this is the external part of the circuit. Real current, not the assumed current. I can assume any direction for current direction, but if you want to go for real, yeah, this is the real current. Real current always flows from positive terminal to negative terminal through external part of the circuit. So this is a real current. So therefore, the voltage drop across the resistor is VR like this. Now, if I apply KVL, we get minus VI plus VR plus 0.7 equals to 0. So that gives us VR is equal to VI minus 0.7. So that is the same shape that we obtained when you see this is the same expression. You see the same expression that we obtained now when for positive half cycle we obtained the same expression. V naught is equal to VI minus 0.7. For negative half cycle we got the same expression. V naught is equal to VI minus 0.7. Now here this is only the magnitude, this is also the magnitude. So that means even we are considering negative half cycle, but the value of V naught we got is what? Positive. You see? Positive. We are going to put the magnitude only. So that means if I draw it again, 0 here, 0 here, and for output it will look like this. For when the diode is on. So that means for positive half cycle, we have it has been rectified. For the negative half cycle as well, it has been rectified. Although its input signal is negative, output signal, its corresponding output signal is flipped. Now, how can it make sense? So notice for positive half cycle, the positive half cycle, the current is flowing in this direction. And for negative half cycle, the current is flowing in this direction. So what does it means? Notice, so current might be different in different direction during the, maybe it's flowing, maybe it's not flowing, but through the resistor, regardless it is positive half cycle or negative half cycle, through the resistor, the current is always flowing in same direction, from right hand side to left hand side. So correspondingly our voltage drop for both positive half cycle and for both negative half cycle is in the same direction. So that's why for positive half cycle we have this, and the negative half cycle this. Okay. Now, so now that we know we have obtained the input output relationship. So what is the difference between the full wave rectifier circuit for full wave bridge rectifier and full wave rectifier circuit, full wave rectifier with the filter tap transformer? Full wave bridge rectifier, we have 4 diodes. So each cycle we had to go through how many diodes? Valanto? Huh? For each cycle, you have to pass through each cycle. Protect cycle altogether there are 4 diodes. Each cycle you have to pass through 2 diodes. So that means if there are 2 diodes, we have to consider the voltage drop of 0.7 here. Also the voltage drop of 0.7 here. So 1.4. Okay. For both positive half cycle and negative half cycle. But here, since there are 2 diodes, for each cycle we have to consider 0.7. So that means for although for full wave bridge rectifier, V naught is equal to VI minus 1.4, and it is for full wave rectifier with filter center tap transformers, V naught is equal to Vi minus 0.7. So the peak is different. And full wave bridge rectifier, we have to 0 to T1, T2. I mean, draw it. Let me draw it here nicely. Well, as nice as I can. So T1, T2, T3, it's like T by 2, T4, capital T. So this is Vm minus 1.4 for full wave bridge rectifier. Full wave bridge rectifier. And full wave rectifier is filter cap center tap transformer. It looks like this. T1, T2, T by 2, T3, T4, capital T. And the Vm is Vm minus 0.7. So that means, you see, we have to give quite a large amount of voltage to the diode. Diode takes away a 1.4 for full wave bridge rectifier. Also, it starts because it takes longer time to turn on, because you have to conduct D1 and then conduct D2 before it starts. So since there's only one diode to conduct, it takes relatively shorter period to turn on, and it takes relatively twice as much. So এখানে যত টাইম লাগে তার থেকে দ্বিগুণ টাইম লাগে to turn on, and correspondingly output voltage is higher. So that means in that case, if VDC, V average, this one 2.318 times Vm minus 1.4 for full wave bridge rectifier, and V average equals to 2 times 0.318 times Vm minus 0.7. Kunta boro? Which one is bigger? This one or first one or the second one?
The first one.
No, first one is smaller, because you see it's Vm minus 1.4.
Yes.
আপনি যদি Vm 10 ধরেন তাহলে minus 1.4 কত? 8.6. and Vm যদি 10 ধরেন এখন কত? 9.3. So we get a higher average value for this one compared to this one.
Yes, sir.
Okay. So these are the and the first one I'm not going to show you these things, because it is essentially a full wave bridge rectifier. Instead of 4 diodes, we have 6 diodes. Here there are 2 diodes. Here there are two diodes. So that means each during the positive half cycle, diode has to pass through how many diodes? 1, 2, 3, 4. তো আমাকে যখন TSB transition state voltage বের করতে হবে, so it will be simply like this. আমি just একটু পর্যন্ত দেখিয়ে দিই। Okay, so a transition state lines, so 0.7, 0.7. So 0.7, 0.7, 0.7, 0.7. So Vi would be what? 2.8 volt. So that means we're going to draw the transition line here. Vi is equal to 2.8. And for negative half cycle, we're going to draw, because since 2 diodes we have to pass through negative half cycle. Okay. Vi is equal to minus 1.4. So that means transition, তার মানে হচ্ছে আউটপুটটা ইনিশিয়াল, তার মানে এটা যদি এরকম হয়, it takes longer time to turn on. It takes relatively shorter time to turn on. So output দেখা যাবে এটা এরকম দেখা যাবে, এরকম অনেকটা, because its peak would be Vm minus 2.8 আর এই পিকটা কত হবে Vm minus 1.4. So although it is rectified, this peak is smaller, this peak is bigger, smaller, bigger, smaller, bigger. This is how it goes. So we have to solve it exactly the same way we solved the full wave bridge rectifier or the this full wave rectified filter capacitor. All right. Any question?